So we get d minus 3, d plus 2, operating on x, plus 2, the whole thing on x is equal to 0. Careful with your brackets and stuff, right? Because we're adding. So we got d minus 3, d plus 2 on x, plus 2. Oh, 2d. Right? Right? I got d minus 3d plus 2 on x, and then I got plus 2d. That whole stuff on x is equal to 0. And now we just expand that and solve it. Okay, so what do I get? So I get d squared, right? Again, you just operate formally, d squared. Then I get a minus 3d plus 2d. Minus 3d plus 2d, that's a negative d, but plus 2d is plus d. Right? That whole thing operating on x is equal to 0. You know, I think I made a mistake here.
Don't you have minus 6 after?
Yeah, that's right. Okay, let's do the d sets. dd is d squared, right?
Yep.
Minus 3d plus 2d is negative d plus 2. That's still plus d, right?
Mm-hmm.
And then, yeah, you're right, I forgot the minus 6. Operating on x is equal to 0. Okay? Now let's just write that in our normal notation so you see what's going on with here. This is really the second derivative of x with respect to t plus dx dt minus 6x is equal to 0. Right? So now we have a second order linear differential equation with constant coefficients, and now you see it just involves x. You know how to do this one, right? The solution of e to the r of t, so the characteristic equation is r squared plus r minus 6 is equal to 0. That's the same as what? I guess r plus 3, r minus 2 is equal to 0. Okay, so the roots of the characteristic equation, the first root is plus 2, and the second root is negative 3. Okay. So now we can write x of t, right? Superposition. Let me just see the way I did it in my notes. Because, you know, I did c1 e to the 2t. Okay. So I get arbitrary constant c1 e to the 2t plus c sub 2 e to the minus 3t. Okay? That's the solution for x as a function of t. But we also have to find y, right? And let me just give you like a little hint over here. It's something that you always should look out for, okay? Let's see. I could use either this or this to get y, because I know x. Let me show you though why this wouldn't be a good idea, okay? Suppose you know x, you do dx dt, right? You put it to the other side of the equation, then you get dy dt plus 2y is some function of t. Now you gotta solve an inhomogeneous equation, and another thing which comes up, unfortunately, is that when you integrate that, you get another constant of integration. But theory says it only should be 2, okay? Look, if you go to the second equation though, things are much simpler. Because you know x, this term is known and this term is known, there's no y derivative in here. So you can solve for y immediately. And that's exactly what we want, right? You don't want to have another constant of integration. So let me just call this equation number 1, equation 2. Okay? So from equation 2, okay, what's y? X dot minus 3x is 2y. So 2y is equal to x dot minus 3x. Okay? And now you just plug in. Okay? So 2y is equal to, what's dx dt? 2c1 e to the 2t minus 3c2 e to the minus 3t. I need a dx dt, which is 2c1 e to the 2t minus 3c2 minus 3t minus 3 times x. So it's minus 3c1 e to the 2t minus 3c2 e to the minus 3t. So we can solve for y finally. Let's see what happens over here. 2c1 e to the 2t minus 3c1. That's a negative c1, so I guess I get negative c1 over 2 e to the 2t. Okay? And what about e to the minus 3t? Minus 3c2 minus 3c2 is minus 6c2, but divide that minus 3c2 e to the minus 3t. Just check, did that correctly? Yeah, okay. So now it's basically that you do have the solution. Here's the solution for x, right? And here's your solution for y. Okay? And again, very important, there's only two arbitrary constants. Okay? So the C1 and C2 here are exact same C1 and C2 that appear over here. Okay? Now again, you could have taken this equation and solved for y of t first. Okay? And then you'd get x. Okay? It would look a little different because then with the y you'd probably have a C1, C2, and then you have the fractions with the other guy, but it's an equivalent system. It's an equivalent solution. Okay? If you apply the initial conditions, you get exactly the same answer. Okay, so this is basically the technique that you do, no matter how many equations you have, so long as it's a linear system and it has constant coefficients. Okay? You transform it from our normal notation to this D notation, kind of look at it and you say, what's the easiest thing to eliminate? Okay? Sometimes it doesn't make a difference, you know. In this case, it was easier just to eliminate y. Okay, you do that operation, you then get an equation in just one dependent variable, which we know how to solve, okay? And then the important thing is when you solve for the other one, try to get an equation that doesn't require you to integrate again. Sometimes you have to. We'll see the last example we're going to do, we have to integrate, and we're going to pick up another constant of integration that we have to get rid of, okay? And unfortunately, the book doesn't emphasize this, okay? I think they do it kind of a circuitous way. They go back and they do the y in the same way. They eliminate again, but it's not necessary, okay? So long as you look at the equations first and determine what the overall order is, you know exactly how many arbitrary constants are in the solution. Okay, so let's go to example number 2 then.
Professor?
Sure. Yeah.
For where you did equation 2 to find y's solution?
Yeah.
For the x where you did dx dt, you just took the derivative of the x solution?
Yeah.
And you plugged it in?
Yeah.
So what did we do with the minus 3x?
That's right.
It's just the other part of it?
Yeah. There's the dx dt, and
Right.
there's the 3x, the last two terms.
Okay.
Okay. Example. So, first equation, dx dt minus 4x, I'm afraid this is going to round 2. Oh, my right one has ink in it there. Plus the second derivative of y with respect to time. So x dot minus 4x plus y double dot equals t squared. And we read that to you again. So the first equation is dx dt minus 4x plus the second derivative of y with respect to t is t squared. Okay, and the second equation will be dx dt plus x plus dy dt is equal to 0. Check that again, x dot minus 4x plus y dot is t squared. Okay. So, what's the order of this system? Okay. Well, in x, if I look at both equations, the highest derivative I see in x is the first, right? What I see in y is second derivative. 2 plus 1, 3. Third order. So order is equal to 3. That means that what? That when I write my general solution to this system, I should land up with 3 arbitrary constants. Again, no more, no less. Okay? Okay, let's see how we're going to do this one. Okay, well, step to step is you just do that D notation, right? T minus 4 operating on x, that's your x dot minus 4x, plus d squared y is equal to t squared. Notice there's a difference between example 1 and example 2. Example 1, it was just first order in x and y, and it was homogeneous, right? Now we've got a non-homogeneous term over here, okay? That t squared. So x dot minus 4x plus y double dot equals that. Okay. And this guy is what? All the x stuff, it looks like d plus 1 operating on x. Right? That gives me my x dot plus x plus dy dt. Is equal to 0. Right? X dot plus x plus dy dt equals 0. I think it's obvious over here that you want to, easiest to eliminate y, right? Because you don't do anything to this and just hit this with the d operator, right? And again, if you wanted to, you could, be masculine, do d plus 1 d minus 4. I don't know why you want to do that, and you get the same answer, okay? But clearly what we're going to do over here is not touch this at all and hit this with the d operator, okay? Okay. So the first equation, I'll just rewrite it down again. It's d minus 4 operating on x plus d squared on y is equal to t squared, right? And when I hit this with the d operator, it means differentiate every term. That's the same as doing d plus 1 on x plus t squared y is equal to 0. Okay. And obviously now we want to subtract, right? Let me just subtract it this way because I like to have quadratics with positive. So I get d squared plus d. Let me just do it slowly. dt plus 1 operating on x minus d minus 4, right? Operating on x. And I see that? I'm subtracting this way. dd plus 1 minus the quantity d minus 4 operating on x is equal to negative t squared. Okay, so what do we get over here? We get d squared plus d minus d plus 4 operating on x is equal to negative t squared. dt plus 1 is d squared plus d. Don't forget that, minus d plus 4. The d's cancel, so we have basically d squared plus 4, right? Let's just write this in our normal notation. The second derivative of x with respect to t, right? Plus 4x is equal to t squared. Okay? So over here now. Everybody knows how to solve that. What is that? That's a second order differential equation.
What happened to the negative sign?
Yes, thank you. Okay? That's a second order differential equation on x, right? With constant coefficients, non-homogeneous. Okay. So this is like practice for the exam, I guess, then, right? This type of equation. Okay, remember what we do? We first solve the associated homogeneous equation, right? And then we add on the particular solution. Okay? So, what about the homogeneous equation? We'll call it x sub c of t. Like, again, and I've said this, of course, many times. Use different notation to denote the solution of the associated homogeneous equation, the particular solution, the general solution. Okay, otherwise you'll get very confused. Okay? Remember, the x of t over here is what? It's the solution to this non-homogeneous equation. Okay? So first we solve the homogeneous equation. That's x double dot plus 4x equals 0. That's an oscillator, sines and cosines, right? Let me just see where I put the constants over here. Cosine first. Okay. So I get c1 cosine 2t plus c sub 2 sine 2t. So that's the general solution of the associated homogeneous equation. And we already used up 2 of our 3 constants. Okay. Now we need the particular solution, right? What's the particular solution? Okay. X double dot plus 4x equals t squared, minus t squared rather, okay? I would do this by the method of terming coefficients, right? What's the family of negative t squared? It's just t squared, t, and 1, right? So, family of minus t squared is just t squared, t, and 1. Okay? And again, what's the first thing you do? Are any of those members of the family solutions of the homogeneous equation? No. Right? It's sines and cosines, no powers. So we don't have to modify the family. Okay. So, x particular is equal to at squared plus bt plus c. And again, these constants, big A, B, C, are not arbitrary constants, right? They're going to be determined numerically by demanding that this be a particular solution. Okay? So, where's my equation there? I have to go up to second derivatives, okay? So what's the first derivative of xp? xp dot is 2at plus b. Okay? Simple differentiation. And the xp double dot is just 2a. Okay? Now, what we do, we plug it in. L operating on xp is equal to what? We need xp double dot, that's the 2a, got that guy, plus 4 times xp. And what's x particular? It's a quadratic, at squared plus bt plus c. Okay? L operating on xp, okay? We obviously want to get all the quadratic stuff together, all the linear. Looks like on quadratic, all I've got is a 4at squared, right? What about linear on t? Looks like a 4bt, right? And about the constants, I've got a 2a, right? And here I pick up a 4c. But we know L operating on xp has to be exactly minus t squared. Okay? And again, a constant, t and t squared are linearly independent. The only way that can hold for all values of t is if the coefficients match. So you find out that what? 4a has to equal -1, or a equals -1/4. Okay? B has to equal to 0, right? There's no t term on the right. Okay? And of course, there's no constant, so 2a plus 4c equals 0, or a plus 2c equals 0. Right? So I get a plus 2c is